is decreasing everywhere between A and B if for any 2 points that we pick, the y value for the one on the left is bigger than the y value for the one on the right. So as we're moving to the right, so from left to right on the graph, our y values are getting smaller instead of bigger. So again, kind of same idea. We have a graph and we're looking between A and B. If you pick any 2 points so that C is to the left of D, then the point at C will be higher than the point at D. So from A to B, we are going downhill. So if we go back to our journey, where are we walking downhill? Mm-hmm. Good.
12.5.
Very good. So we're decreasing. From 3 to 5. From, what'd you say, 8 to 10. And from 12.5 to 15. And then there's one final possibility, which is that we're not going up or down, that we're walking along a straight path, so a flat path. So we call that constant. We've seen the constant function before, right? Which is just a straight horizontal line. So a function is constant between A and B if for all C and D in between A and B, the y value at C is equal to the y value at D. So from A to B, any 2 points that you pick will have the same y value. And so if that's true for all the points between A and B, then it just gives us a horizontal line. That's sort of horizontal. Tilt your head a little until it's horizontal. So going back, where am I walking on flat ground? James, what do you think?
5 to 8.
Very good. So from 5 to 8. And one thing you can notice is that we are always either going up, down, or straight, right? So everywhere on our journey is accounted for by one of these intervals, but they can't overlap, right? It's impossible to be both increasing and decreasing. So if you look at our intervals, we go from increasing to decreasing at 3, and then we go from decreasing to constant at 5, and then we go from constant to decreasing at 8, and decreasing to increasing at 10, and then back from increasing to decreasing at 12.5. So there are no gaps and there are no overlaps. And that should always be the case. If you talk about all three of these things, your intervals should not skip anything. So where one interval ends, the other one begins, so that you're covering the entire domain of your function. And also notice that we're only talking about x values here. The y values don't come into play because if I gave if I said this is like 50 and this is like 30 and we'll say this is like 15 and that's like 25 or something. Picture not drawn to scale. If I said that it was increasing from 25 or from 0 to 50, that's saying, I think I'm talking about this right here, right? But isn't the entire graph between 0 and 50 in terms of y values? So if I said it's increasing from 0 to 50, that would be saying that it's increasing everywhere because all my y values are between 0 and 50. And so when we talk about y values, it's not specific enough because there's multiple places on the graph that could have the same y value. Whereas when we talk about x values, because it's a function and there's only one output for each x value, it's very specific about exactly where on the graph we are. Just like if we were taking this hike, we could talk about, if I said I'm at a height of 50 feet, well, there's only one place. If I said I'm at a height of 30 feet, I could be at two different places along my journey. Well, I could be at lots of different places along my journey, right? But if I say I am 5 miles into my journey, then I know exactly where I am. And there's only one place I could possibly be. And so typically, we always talk about x values whenever we're talking about anywhere specific on a graph. The only times you will use y values are when you're talking about the range of a function or if they ask for the value of the function. So the value of the function at a point is always the y value of the function. So now that we've gone up and down and up and down, we can talk about specific points along our journey. So we want to talk about the points where we're at the top of a mountain or at the bottom of a valley. So mathematically, we call those minimums and maximums. So first, we will define a maximum. So a function has a local or relative. Those are just two words that mean the same thing. Maximum at x equals c if for all a and b such that c is between a and b, f of c is greater than f of a, and f of c is greater than f of b. So what that is saying is that I have a maximum at a specific point if for all points that I choose on the left and right of it, the y value at c is bigger than the y value at those other 2 points. So in English, it's higher than all the points around it. So, do you have a question, William? Okay. So I like to think of it as just like the top of a mountain. So another way you can look at it is if it's a local maximum, you are increasing into it and you're decreasing out of it. So we have one local maximum right here. because we are increasing up to that point and decreasing after that point. There's one more local maximum. Where is it?
12.5.
Yeah, at 12.5, because we are increasing into that point and decreasing out of it. Notice that we do not have a local maximum here, because although we are decreasing out of it, we're not increasing up to it, right? So it can't be flat when you look to the left. It has to be going down on both sides. So we have a, I don't want to erase those, we'll do it up here. We have a local maximum at x equals 3 and 12.5. We sometimes do talk about the y values of our maximums and minimums, and when we talk about the y values at maximum and minimums, we call them the local maximum of the local maximum value of the function. So when we talk about the value of the function, that tells us that we're looking for y values. So if I say the local maximum values, so that's talking about the height that I'm actually at those points. So I have a maximum value of 50 and another one of 25. So those are just the y values of those points. One way you can think of it is the x values are where the maximum occurs, and the y values are what the maximum is. So if we're talking about taking a hike, we could be like, I got to the top of a mountain at 3 miles along my journey. That's where it happened. And then be like, I was at 50 feet. That's a really low mountain, but the top of the mountain was 50 feet in altitude or 50 feet high. So what that height is your y value. Where that height occurs or where that maximum occurs is your x value. So we should talk local minimums too. So a function has a local or relative minimum at x equals c if for all numbers around c, so to the left and right of c, the y value at c is greater than both the y value at A and the y value at B. No, it's not. I was copying what I wrote for the other one. It's a minimum, so it's less than, not greater than. It is lower than all the points around it. I'm sorry, I started copying and then got carried away. So a minimum is lower than all the points around it. And notice that we're not talking like when we had two local maximums. So we're not saying that the y value at that point is necessarily higher than all of the y values on the function. We're just saying that it's higher than all of the points in the immediate area, right? Because we had a local maximum at 12.5, which definitely isn't higher than all the points on the graph, but it's higher than all the points around it. So looking to the left and looking to the right, it's going downhill, even though it's not the highest point on the graph. So where do I have a local minimum? At 10, right? So the bottom of a valley. So that means a local minimum occurs if we are decreasing into it and increasing out of it. So at x equals 10. What is my local minimum value?
15.
Good. Is 15. So I obtain a minimum value of 15 at 10, or at x equals 10. So right here. Notice again that this point right here is not a local minimum, because although we are decreasing into it, we are not increasing out of it. So we don't go back up as we come away from that point. You can also, if we look at where our function is increasing or decreasing, notice that the local maximums are the places where I go from increasing to decreasing. And the local minimum is where I go from decreasing to increasing. So those are sort of the new things that we're going to talk about. So we're going to spend the rest of our time kind of just analyzing the behavior of graphs. So we're going to see some stuff that we've already done, like where the graph is positive or negative. But these are the new components that we're going to incorporate into that. Any questions so far? Does this make pretty good sense? Again, when in doubt, just start at the left side of the graph and think of walking along it and whether or not you're going uphill or downhill or straight, whether you're at the top of a mountain or the bottom of a valley. So one place this type of thing is helpful in is when we have application problems. So in this situation, we're talking about like a room, and we want to portion off a corner of the room to make like what, a testing area? Yes, a testing center. And they're saying we have a total of 30 feet of dividers, which we can presumably cut anywhere we want. And so we're going to make a rectangular area in the corner. And we will say the width of that area is x. Well, then the length is whatever I have left of my 30 feet after I make the width, right? So it's going to be 30 minus x. And then the area is what you get when you multiply those, which is given by that area function there. And what we want to know is what width will maximize area. So if we look at the graph of our area function, what should the width of my rectangle be if I want to maximize area? So 15, because my local maximum is at the point 15 to 25, and I said x was my width, so I use the x value of that point because I'm looking for the width, or x value, which will maximize my area. So my width is 15 feet. What would the length of my rectangle be then? Really, I'm not getting tangled up in wires, I promise. What would it be?
225.
So would that be the length of the rectangle, so the other dimension? Right here?
No.
What would that be?
15.
That would be 15, right? Because I have a total of 15 feet. So if I use 15 feet for the width, I only have 15 feet left for the length. What is that 225? So it's the y value of a point, and the point is on the graph of what function? Yeah, so our function is an area function, which means its outputs are area. So the y values on this graph are the areas corresponding to each width that I could make for my rectangle. So the x values are the width of my rectangle, and the y values are the area of my rectangle. And that's one of the reasons I've talked so much about when we do these application problems, just labeling everything, because we're starting to get into the problems where we have more than two unknowns. So when we have multiple unknowns, we kind of have to go back and forth and figure out what each number represents, because it's not just like, well, I found one of my unknowns, so the other number must be the other one, because we're going to have multiple unknowns. So the maximum area that I can make is 225. Whoops, got carried away. 225 square feet. So the maximum value of my function is 220 feet, or 225 square feet, and it occurs at a width of 15 feet. So let's look at the graph of g of x. So this is essentially the same as when we thought about going on our hike. You just want to think of moving across this graph from left to right, and we're going to look for all these same things. So can somebody tell me what one of the local minimum values is? So the point is -8, -4. Good. So we have one point right here. What is the value of the function there? Yeah, it's -4, right? Because the value of the function is always the y value. Oh my gosh. You guys get pictures of the graph too. I didn't do it at the beginning because I didn't put our height on here and I didn't want you guys to be upset with what we did. It's going to make it so much easier. There we go. Okay, that's better because I'm going to cover up all sorts of things as I draw on this. So the value of the function is our y value. So one of our local minimum values is -4. What is another one of my local minimum values? 0, good, because I have a local minimum here and I have a local minimum here. Both those have a value of 0. And I don't have to list that twice, even though it occurs at more than one point. So what are the values of x at which my local minimums occur? Mm-hmm. So what the values are y's. That's the y value of the function. And where the values occur are x values. So what are my local maximum values? Mm-hmm.
6.
Yeah. and 6. Very good. So those are my local maximums. What are the values of x at which those maximums occur?
-2, 2.
Very good. And it's kind of nice to do those first, because then when you do increasing and decreasing, you're just looking at the intervals in between the minimums and maximums, because those are the points where it switches. So where is my function increasing?
-8.
So from -8 to -2. Very good. Where else?
0 to 2.
Perfect. And?
5 to up.
Yeah, so since there's an arrow, it's a tiny arrow, but since there's an arrow on the right, we just say 5 to infinity. Whenever there's arrows on the ends of functions, we just assume that the function continues in that direction. Like, there won't be like another place where it turns around later on that we just don't see. We assume that it just keeps going in that direction. So let's see, from -8 to -2, and again, these are always x values. From 0 to 2, and from 5 to infinity. Where is my function decreasing? Good. Where else?
-2 to 0.
Good. And?
10 to 5.
Good. And remember that we always want these to be our x values. So negative infinity to that first point, which is at -8, right? So negative infinity to -8. And then the x values in that second area are -2 and 0. So from -2 to 0. And then that last one is +2 to +5. And you can kind of see like these like fill in the gaps in between where we were increasing. And that can help you if you check for that. That can help you because it's so easy to accidentally slip a y value in there. So if we had accidentally used a y value, we could catch that by noticing, like, if we put a 10 instead of a 2, that 10 isn't where it stopped increasing, right? It stopped increasing at 2, and so that can help if we check there's no overlaps. What's up?
So, like, I know I'm kind of stupid and everything.
No, you're
but,
not.
Like, I would, like, isn't, like, the x value in the second place in the parentheses and the y value in the first place?
So these are intervals, not
So
ordered
they're-
pairs.
So they're all x
They're all
values.
x values,
Okay,
yep.
that makes sense.
That was a good question.
'Cause I've been, like,
Don't say
I've been,
that
like,
about
wondering, like,
yourself.
This whole time I'm like, did I learn math wrong in high school?
No, they look exactly the same. We just have to, in context, whenever we talk about intervals, we're talking about just x or just y.
So you're never just gonna, like, throw something on the test with no instruction, right?
Right, oh no. And then if we're talking about points, then that's an x and a y. So where is g of x equal to 0? Uh-huh. So here, and here, and here, and one more. Yep, good. So one thing about the graphs that we give you is like often we'll label certain points just so you don't have to squint and try to figure out like what the y values are. But every point on that graph is a point. So it's not just the ones that we mark that are points. Everywhere along the curve is a point, even if we don't label it or put a dot there. So at x equals -10, -5, 0, and 5, the y value is 0. And then for this last one, I want to erase all this so we can see it better.
Does it matter if, like, do you have to go in, like, increasing value, or you can just throw them on there?
Yeah. So yeah, that's just a list of y value or x values, so the order doesn't matter. Okay, so now we want to talk about where g of x is greater than 0. So remember, g of x is an output, so that's our y values. So we're looking at where our y values are above the x-axis. So if we start all the way at the left of the graph, are we above the x-axis? So all the way at the left, g of x is greater than 0. So we can just walk along the graph until it stops being greater than 0. And then keep walking until it starts being greater than 0 again. And then it never goes below the x-axis again, right? However, we have to be a little bit careful because this is a strict inequality, so we don't want to include the points where y is equal to 0, which means those points where it touches the x-axis have to be open points. So I'm going to have an open point here, an open point here, an open point here, and an open point here. So when I write my intervals, I need to skip those x values because at those x values, the y value is not greater than 0. It's equal to 0. So g of x is greater than 0 from -infinity to -10, not including -10, from -5 to 0, not including either one, from 0 to 5, again not including either one, and then from 5 to infinity. So if I had instead asked where g of x is greater than or equal to 0, then we could have included these points that are on the x-axis. So we would say from -infinity to -10, including -10. And then we start up again at -5. And we don't have to skip the points where we like bounce off the x-axis. So then it goes all the way to just infinity. So we didn't need multiple intervals there because we didn't have to skip those individual points. Does that make sense, the difference between those two?
Intervals, why don't you use brackets when you're including like just x points on the graph? Like why do you use the open brackets?
Because we're not including the endpoints.
Okay.
So down here, we're not including -10, -5, 0, and 5, because those are the points where g of x is equal to 0, and we only want the points where g of x is greater than 0.
So even with the intervals too, where it's increasing from -8.
Oh, yeah, so this is it's a constant battle between applied mathematicians and pure mathematicians. I'm a pure mathematician, so I'm going to do it as a pure mathematician. And our argument is that, You can't be both increasing and decreasing anywhere. So if I included, say, 2, then I'm saying that at 2 I'm increasing and I'm also decreasing. Neither of which is actually true. At 2, I'm not going up or down. I'm standing still at a single point, right? So there are arguments both ways. Applied mathematicians think of things like, well, you have to always be increasing or decreasing. So if we're talking about something like time, we can't say that 2 seconds doesn't exist. We can't say we just skip over 2 seconds, so we have to include it somewhere. But pure mathematicians recognize that you can't be going up and down at the same time, and so we don't include them. For these particular, only those problems, my math lab will accept either one, but it's only for those ones that it'll accept either one. And that's just because there's a couple schools of thought as far as what actually happens at the turning points. So that's a good stopping place. If after you do your homework tonight, you guys are feeling like you want to go over this a little bit more, then we'll do that second graph that's on the back of that sheet tomorrow. But you can kind of gauge how comfortable you feel with it tonight as you do your homework, and then just let me know if you feel like we need that time on that other one as well. Whoa. So you do have my math lab tonight, and then you've got a worksheet as well. Have a great Thursday. It is Thursday, right? Okay.
Last day of February.
Yeah.
Last February, the teens.
Oh, that's right.